Hi everyone. My name's Tom Geraghty. I'm EMEA Transformation Lead at Red Hat Open Innovation Labs. I've been working with technology teams and organizations for nearly 20 years. And my key areas of focus are around DevOps and ways of working, lean and psychological safety. Outside of work, I ride mountain bikes, I practice yoga, and I like to travel a lot in normal times. Oh, and incidentally, I love Lisbon. My partner and I spent a few weeks there in 2019, and we discovered a little place that did the most amazing bifana called O Trevo, and I can't wait to go there again. Red Hat, you may have heard of us. We're the world's largest pure play open source business. And if I may say so myself, Open Innovation Labs is the coolest part of Red Hat, where we work with organizations to help transform and improve teams and organizations using open processes, culture, and technologies that help drive business performance and resilience. And as part of Open Innovation Labs and the transformation team, I also work with these fine gentlemen, some of whom you may have heard of from such books as Web Operations, the DevOps Handbook, and the Phoenix Project. So today, we're going to be talking resilience engineering, DevOps, and psychological safety. So if you're already familiar with the CALMS elements of DevOps, culture, automation, lean, measurement, and sharing, you'll see some interesting and cool alignments with resilience engineering. Resilience engineering is a huge field, and I'm not an expert in it, but I do think it's a really valuable field of practice for us in the tech and DevOps domains to learn from and contribute to. In fact, I'm almost certainly going to get something or a number of things wrong in this talk. So if you spot an error or want to help me back on track, get in touch. Incidentally, most of these slides have my Twitter handle on, not this one, but most of them. And that's probably the best way to contact me. But you can also find me on LinkedIn and you can email me at tom@redhat.com. I'm always up for geeking out about DevOps and resilience engineering stuff. Oh, and I also love it if people take photos or screenshots of presentation and tweet them or share them on LinkedIn. And so if you want to do that, please go ahead. Now, I sincerely believe that resilience engineering, or something very like it, represents the next phase for transformation and evolution of organizations. And in this talk, I think we'll see why. And in fact, I think we'll see why in Eduardo's talk as well. But to begin with, I'm going to ask you to think about a submarine that contains technology, fuel, armaments, radar, supplies, control systems, escape pods, medical equipment, spare parts, and around 150 people. This submarine has to operate at sea for months at a time, carrying out exercises and operations, but it also has to deal with surprises, challenges, unexpected events, or even attacks. And this particular submarine is the Santa Fe, commanded by David Marquet, who wrote Turn the Ship Around. Now, in this book, Marquet in his life, he wrote the book afterwards, Marquet acted like any other captain until one day he unknowingly gave an impossible order and his crew tried to follow it anyway. And when he asked his crew why the order wasn't challenged because it was impossible, the answer was because you told me to. And Marquet realized that he was being a leader to an organization of followers who would simply try to blindly follow orders rather than lead themselves, speak up, admit mistakes, or learn how to be better. Turn the Ship Around, his book, is the story of how David Marquet took the Santa Fe from the worst in the fleet to the best in the fleet by challenging the US Navy's traditional leader-follower approach. Now, keep thinking about this submarine because it's a useful thing to think about through this talk. This is Lauren Hochstein. He's a senior software engineer at Netflix, and he's very active in the academic field of resilience engineering. He's really worth following on Twitter if you're into resilience engineering, complex systems, and hot takes on root cause analysis. In DevOps, we talk a lot about agility, change, responsiveness, and we put a lot of effort into agile, Scrum, and product and delivery and DevOps practices to help teams perform better and be more responsive to change. But what about the wider organization? Do you feel like organizations, especially once they've reached Dunbar's number of 150 or so, are really agile? Are they really responsive to change? How do they react when they're faced with a big challenge, like a huge market disruptor dropping in, a brand new competitor, or global pandemic? Do they even see those things coming? Can they quickly detect, change, and adapt to surprise? Do they effectively learn from those challenges and embed that learning? This session is going to talk about that scale of things, the complexities of big systems and change. Now, Scott Sagan, he's a key figure in safety and complexity. And in his book called The Limits of Safety, he describes how organizations, particularly the US military during the Cold War, became too relaxed about the precautions that they had in place against mistakes and accidents in respect to the enormous power they created in nuclear weapons and ballistic missiles. And of course, they denied it, and there was a shroud of secrecy around military operations, so it was hard to disprove them. But Scott Sagan investigated through freedom of information requests and interviews with retired personnel, and found that particularly during the Cold War, things like routine satellite tracking, civilian amateur rocket tests, faulty equipment, or simply equipment that was difficult or confusing to use, the risk of an accidental nuclear superpower confrontation, i.e. global thermonuclear war, for those of you who have watched war games, was over 50% during that period. What Scott Sagan is saying here is that during that time, we were more likely than not to completely destroy the world as we knew it by accident. And now think about this term: there is no root cause. Resilience engineering shares a domain with safety culture, that of Scott Sagan, and you'll often hear resilience engineering proponents use the maxim, there is no root cause. And Sidney Decker's book, The Field Guide to Understanding Human Error, is a great book to dive deeper into this concept. Now, systems are generally very well protected against simple failure, but think about the Challenger disaster, Chernobyl, a Nagasaki train crash, the Beirut explosion, or the 2008 financial crisis. They're big, complex failures. And the Beirut explosion on the 4th of August last year, as this photo is of, is no different. 204 people died in this. And the primary blame for the explosion was placed upon the Beirut Port Authority and Lebanese customs for leaving nearly 2,750 tons of highly explosive ammonium nitrate in a hangar for nearly 7 years in unsafe conditions. Many people, including the Ministers of Finance, Justice, and Lebanon's President and Prime Minister, knew that these volatile materials were stored there in years and months before the explosion. The result of the explosion was actually the result of a fire ignited by sparks from a welding works on nearby metal door. Now, there is no root cause, but there are many component causes. If someone had raised a concern and had been listened to, if the conditions for storage had been proper, if the welding hadn't been required to be done, if the explosives had been distributed differently or stored somewhere else, it wouldn't have happened. There are multiple myriad causes for everything. And even worse than that, if we try and search for a root cause, when this false root cause is found, it tends to shut down any further discussion and exploration because we think we've found all there is to know. And that leads to resilience engineering. This slide is actually adapted from one of John Allspor's talks, who I recommend following and learning from if you're further interested in the field. Now, resilience engineering is made up of researchers, practitioners, and contributors in all of these areas, from biology, sociology, ecology, complexity science, and cognitive psychology. We need to address also this word engineering, because it's not really engineering in the sense that you would normally use it. It's not software engineering or civil engineering, though it may well expand into those fields. It's more about engineering in the much wider sense, in the way that you would engineer a situation, an organization, or even an entire nation. So we mentioned safety before, and I can't speak about resilience engineering without mentioning Eric Hollnagel, who coined the terms safety 1 and safety 2. Now, safety 1 refers to approaches that try to avoid failure in systems and investigates when a failure occurs by trying to find out what went wrong and fix it. There's a tendency to look for that root cause, which could mean missing the broader causes. Safety 2 The alternative is about looking at successes and creating systems and cultures where failure occurs less often, they're more safe, through things going right more often. So they're looking at successes. So as well as talking about the word engineering, we're going to need to talk about the word systems. And this is Dave Snowden's Cynefin framework. Cynefin is the Welsh word for habitat. And while we're talking about these, keep thinking about that submarine. Now, look at this diagram. This is the Cynefin framework. If you start at the bottom right, systems, simple systems, are fairly easy to deal with. In simple systems, there are no unknowns. They're fixed and repeatable in nature, and the same process achieves the same result each time, so that we humans can use things like standard operating procedures to work with them. And a good example here might be a Lego model. You don't need any prior experience, and just following the instructions will get you to a complete Lego model. If you move up to the top right, however, and you get into the realm of complicated systems, these are large, usually too large for us humans to hold in our heads in their entirety, but they are finite and have fixed rules. They possess known unknowns, by which we mean that you can find the answer if you know where to look. Things like a modern motor car or a game of chess are really complicated, but they possess fixed rules that do not change. With expertise and good practice, such as employed by surgeons or engineers or chess players, we can work with these systems. Now, if you move left to the top left into complex systems. Complex systems possess unknown unknowns. And these include realms such as battlefields, ecosystems, organizations, and teams, or humans themselves. Complex systems are complex because they contain people, living things, and we call them socio-technical systems. The practice in complex systems is called probe, sense, and respond. Because complex systems resist reductionist attempts at determining cause and effect because the rules aren't fixed. So the effects of changes themselves change over time. And even the attempt of measuring or sensing in a complex system can affect the system itself. And we'll come back to this later. When working with complex systems, feedback loops that facilitate continuous learning about a changing system are crucial so that you can continue to understand the system. This is about running experiments, probe, sense, and respond. Now, bottom left, chaotic systems. Chaotic systems are impossible to predict. They include things like emergency departments or crisis situations. There are no real rules to speak of, even ones that change. And in these cases, you simply have to act. Just act first. And communication is rapid and top-down or broadcast because there's no time or indeed any use for debate. That central point in this diagram is that white gap in the middle is where is where confusion lies, because that's where you're trying to work out what system you're actually in. And on the right is the realm of explicit knowledge that can be described in instruction manuals and operating procedures. On the left is the realm of tacit knowledge, that of expertise and experience. Now, resilience engineering largely, though not exclusively, applies to complex systems. And this is largely in relation to complex systems that contain people, i.e. socio-technical systems. And socio-technical theory has at its core the idea that the design and performance of any organizational system can only be understood and improved if both social and technical aspects are brought together and treated as interdependent parts of a complex system. So back to John again. Resilience is the ability of a system, the socio-technical ones we're part of, like businesses, communities, and societies, to adapt to unforeseen, unanticipated, unexpected, and unlikely events and challenges. Of course, they might not be challenges, they might be opportunities. But without that sustained adaptive capacity, which is the continued ability to change fundamentally, a system can't effectively take advantage of them. And since, at the current time, the technical elements of a system cannot truly observe, anticipate, detect, and learn, it is people that are the adaptable elements of a system. And so remember this term, sustained adaptive capacity, is an excellent and concise description of resilience. So now we're really finally talking about the word resilience. And when we talk about designing highly available systems, we often cover techniques such as redundancy, retries, fallbacks, and failovers. We think about what might go wrong, things like server failure, storage units filling up, or network congestion. And we design our systems to gracefully handle those situations because we know they might come up. Now, David Woods, who created this, is a professor at Ohio State University, where he's the lead for the Initiative on Complexity in Natural, Social, and Engineered Systems. And he's a co-director of Ohio State University's Cognitive Systems Engineering Lab. And he uses the word robustness to refer to systems that are designed to effectively handle known failure modes, things like network failures or storage filling up. Resilience, on the other hand, describes how well systems can handle troubles that were not foreseeable by the designer. You can think of robustness as being able to deal with the known unknowns, like those in complicated systems on the right, and resilience as being able to deal with unknown unknowns, as in complex systems on the left of the Cynefin framework. So think back to that submarine and what components comprise robustness and what components might confer resilience. So we have technology, we have fuel, armaments, escape pods, medical equipment, and spare parts, and they all contribute to Woods' concept of robustness. But we also have 150 people, and those people confer resilience because it's people that can change and learn, not technology. So keep thinking about that submarine, and we'll keep going back to this. Now, David Woods, who we just encountered, clarifies resilience further by explaining this. Resilience is something you do, not something you have. So you do resilience. Resilience is a verb. You, your systems, and your organizations do resilience through the 4 activities of anticipation, detection, response, and learning. We're going to keep coming back to these 4 activities, this anticipate, detect, respond, and learn in that sequence. Jay Bloom, one of our GTO team at Red Hat, reframes these capabilities a bit here, and he shows that anticipation, detection, and response are capabilities or activities based upon the foundations of a learning organization. He also highlights that efficiency, and you could also crowbar in the word effectiveness here, is a factor. The cost of change, our risk appetite, our ability to do more with less, the amount of toil we deal with, toil being non-value generating work. And fundamentally, practices such as platform and technology all affect our ability to learn, and therefore our ability to anticipate, detect, and respond. And in fact, regards efficiency, because there's a really interesting tension here between efficiency on one end of the scale and resilience on the other. Efficiency comes through an optimal adaptation to an existing environment, while resilience requires the capacity to adapt to disruptive changes in the environment. Now, optimizing for efficiency reduces a system's ability to respond to change. For example, you can make a car that's super efficient in a straight line on a motorway, but that optimization soon hinders the ability of the car to maneuver quickly, work off-road, carry large loads, or survive a crash. And the same applies to submarines. Well, I'm no expert on submarines, however much I bang on about them. There's a tension between how efficient the entire system can be and how responsive and resilient it can be. And what does that tension mean in practice? Well, amongst other things, it means you need some slack in the system, also known as a buffer. It's worth noting that that buffer could also add complexities as well, and it may only be introduced in hindsight. And it may also be vulnerable to efficiency pressures and like lean kind of efforts that may view slack as waste or underutilization, but it is essential to resilience. This is a great graphic from an article by Tarcísio Sorin from the Federal University of Rio Grande do Sul in Brazil, which is available on the Resilient Engineering Association website, which is definitely worth a look. So let's zoom out for a minute. We've dived right in. Let's zoom back out. This is this, if you like, the resilience scale from low to high. At one end on the left, we have low resilience, fragility, brittleness, very little capacity to cope with failure or challenges. And then we move into robustness, which is the ability to cope with known unknowns, like server failures or a flat tire. Resilience is the ability to cope with unknown unknowns. Indeed, true resilience through learning means that you can actually improve as a result of challenges and failures by adapting your thinking, your operating model, or even your business model. True resilience, therefore, means actually getting better through adversity by learning and adapting and continuing to do so. And this means that challenges are also and always opportunities for learning. And this is reflected in this, and this is a great example in real life, is bone. This is Dr. Richard Cook, and he's got a great talk about the resiliency of bone. And in fact, on the right there, that's my left arm, and this is also why mountain biking can hurt you. Dr. Richard Cook is a principal with Adaptive Capacity Labs and a research scientist in the Department of Integrated Systems Engineering at Ohio State University. And he's a real expert in resilience engineering and socio-technical systems. And he refers to bone as the primary example, the archetype, if you like, of resilience and resilience engineering. When bone breaks, it actually gets stronger through healing. You can see this in the right. You can actually see, so this is 2 breaks. The pins in my arm, this is my radius and ulnar with the 2 plates and screws in. That was an older break. And the break in my elbow with the pins going in, that's almost a brand new break because it's just after the operation. And you can see the gap in the bone there. Now that gap is the bone is going to heal in there, and you can see in the older break with the plates, it's healed already and it's stronger than it was before. This regrowth to stronger takes energy and effort, and the extra strength strikes a balance between competing demands. Too strong, and it's not worth the energy and extra weight that it demands, and it could cause weaknesses elsewhere. So it's a finely tuned approach. It's the bone's ability of being able to detect a break in the first place, respond by filling the gap with osteoblasts, the bone cells whose role it is to create new bone, and adapt to challenge by healing back stronger. And this is such a great example of resilience and sustained adaptive capacity. So bone may break, and it will get stronger through healing for as long as you're alive, and everything else being well, it will keep growing back stronger than before. So let's think about non-resilience for a moment. What does not being resilient look like? Well, Blockbuster was a super robust business. It was geographically dispersed. It had a great business model, good supply chains, and a solid cash position. But they did not have the capabilities to anticipate the market changing, detect the change, respond to it, and learn from it in order to survive in a changing world. And now I believe there's just one lonely Blockbuster store left in a town in Oregon, in America. So back to Jabe Bloom again, this time about learning from those changing circumstances and challenges. Jabe can be a bit verbose at times, but what he's saying is here, that a resilient organization, a learning organization, is where everyone in it is constantly learning and improving in order to adapt to challenges and complexity. So what do we mean by a learning organization? Well, this is a paper co-authored by Amy Edmondson of psychological safety fame. This was written before Google's Project Aristotle and was actually used as part of Google's project that ended up finding psychological safety to be the most important factor in high-performing teams. And in this paper, Amy and the other authors describe how in order for an organization to identify challenges and opportunities, learn from experiments and mistakes, those experiments that you conduct in complex systems, indeed, carry out those experiments and adapt to the unpredictable. Teams within that organization require high levels of psychological safety. So what we're saying is, with the right foundations in place, an organization can become a learning organization, which is analogous to a resilient organization. So at this point, we really need to reaffirm that resilience engineering is about people. And I love this quote about what resilience engineering is from Nora Jones, CEO of Jelly.io. And she says, it's identifying and enhancing the positive capabilities of people in organizations that allow them to adapt effectively and safely under varying circumstances, which is learning, right? So we now know that what resilience engineering is, why we might want to do it, and how it works. And now we're going to look at some ways to do resilience engineering, or at least facilitate better resilience in our teams and organizations. And just as Soren showed, without slack, without a buffer, resilience is really difficult or impossible. This is the only graphic you'll see in the book, The Phoenix Project. And it shows how above a utilization of around 80%, this is about people, wait time increases exponentially, which means that people need to have free buffer time in order to respond to events and challenges. And you can calculate this quite easily by dividing the amount of time utilized by the amount of time free. So if you look at 50% committed, 50% utilized, you divide 50 by 50, you get 1. That's analogous to 1 minute. If you divide 90 by 10, you get 9. So that's 9 minutes on the chart there. If you divide 99 by 1, then you get 99, which is how to show that any utilization above 80% means that people will not be able to respond to anything, much less any challenges. Now, we also need to manage cognitive load. And I'm sure you may have come across this before, but I'm going to go through it again just in case. Intrinsic cognition is the stuff you know, like how classes are defined in Java or how many IP addresses are represented by 255.255.2550. Extraneous cognition is the stuff you don't know, and the stuff you need to go and find in documentation, work it out, ask someone else, or learn a new tool. This is a simplification, of course. Germane cognition is problem solving, the really valuable bit. So what we're trying to do is maximize or give the most space to the germane cognitive capacity. So Manuel is going to be probably screaming his head off at this, but what we're saying here is that we need to right size the software, we need to right size the teams, we need to make sure that the cognitive capacity in one person's head and the aggregation of that in a team represents or is more than what they need to get the job done. So the capacities cannot be exceeded by the size of the domain that person or team is expected to work with. Otherwise, they can't respond to those challenges. Now, we also need to manage technical debt. The average organization wastes 23 to 42% of their development time on technical debt. This is from a recent study by Adam Thornhill at CodeScene. Now, technical debt slows you down. It makes problems harder to solve by making systems more brittle, harder to change, harder to fix and repair, and harder to diagnose when an incident occurs. Technical debt also results in more and more unplanned work. And of course, unplanned work always takes priority over planned work. So in order to be responsive, adaptive, and have the capacity to quickly and easily change course and learn, we must minimize our technical debt as much as is sensible. We will, of course, always incur technical debt, and there's no need to feel like all debt is bad. And in technology, we're also quite good at, we are pretty good at looking inwards through monitoring and alerting tech metrics like load, availability, volume, and rate and stuff. And we're getting even better at predictive analytics. And there are a load of excellent tools to do that. But we also need to get better at looking at our own organization and our people, and especially at external observability, things like looking at the market, the economy. And if you think back to that anticipate, detect, respond, and learn process, if we're not looking outward, we can't anticipate challenges if we can't see them coming. And this is absolutely crucial as well. We need to work at blameless root cause analyses or post-incident reviews or post-mortems and recognize, back to the start, there is no root cause. Now, this is an example from epidemiology. This is about complete causal pies. So the causal pies contain component causes, many different component causes for an incident to occur. The power of this is recognizing that there are multiple different whole pies, multiple sufficient causes consisting of different sets of component causes. There is no single root cause. And of course, we should learn from incidents. All incidents are a learning opportunity, so treat them like a gift. Concepts such as chaos engineering also come into play here, where you're really just creating those learning opportunities for yourself. But you should also do them for successes. And this is a huge area, one of the most important elements of resilience engineering. In fact, a really useful approach is to look for incidents that were genuinely surprising, ones where you really could not have foreseen them at all, where they're the real unknowns. And particularly valuable are the Goldilocks incidents, where they were not hugely severe, but were not minor. That sweet spot in the middle, the Goldilocks zone. Because studying into incidents that had a really big impact, although they might have a lot of value, they can get derailed or impacted by political or other pressures that inhibit deep and honest introspection or investigation. So concentrate on those incidents that you can genuinely learn from. And make sure that you also identify and learn from the elements that mitigate the impact of the incident and help you survive it. Because by doing that, you're examining both failures and successes at the same time. which if you remember safety 2 as well as safety 1, safety 2 looks at how valuable successes were. Mandy Walls and at PagerDuty and John Allsport both have some amazing resources about conducting systematic postmortems if you go and hunt those out. Also, running fire drills is really valuable to build resilience. This basically means practicing emergency or critical, chaotic, if you remember the Cynefin framework, scenarios. And this does two things. It means we can identify improvements to the processes and tools and practices used in those emergency cases by playing them out as if they were real. But we can also, if you think back to cognitive load, maximize germane cognition by reducing the extraneous cognition for people when that event actually happens. Because this means that when people can deal with the stuff hitting the fan more easily and apply that germane problem solving to actually solving the problems in the moment and learning from the challenge afterwards. Now, again, team topology stuff. So this is a whole talk in itself and kind of overlaps with the concept of cognitive load, but this specifically speaks to Conway's law. The systems that an organization creates will reflect the communication structures of an organization. So fundamentally, an appropriate team and organization structure facilitates reduced context switching, low latency, and high bandwidth communication between teams, and rapid decision-making, fast change, and collaboration. These capabilities, defining team types and team interactions, fundamentally enable resilience because they enable rapid decision-making, communication, change, and learning both inside and outside teams. Now, arguably, in my opinion, most important of all in improving resilience is increasing psychological safety. Dr. Amy Edmondson, who I mentioned before, defines this as a shared belief that a team is safe for interpersonal risk-taking. She sort of discovered and sort of defined psychological safety by studying clinical teams back in 1999. When she found that the best teams, the ones with the most good outcomes, like people surviving and fewer people dying, made more mistakes than the teams with bad outcomes where more people died. That didn't make sense. Why was it true that the best teams made more mistakes? And by investigating more, she found that the best teams admitted more mistakes. So she then defined psychological safety as a belief that one will not be punished or humiliated for speaking up with ideas, questions, concerns, or mistakes. It's a group phenomenon that facilitates people expressing their creativity, talents, and skills without self-censoring and self-silencing. It means being able to run safe-to-learn experiments like those in complex systems, to feel safe delivering news that the recipient might not want to hear, expressing diverse opinions, asking for help, and admitting mistakes. And Sidney Dekker, who we came across previously, found the same thing with airlines. The airlines that report more incidents actually have a lower passenger mortality risk. So we see there's an inverse correlation between the number of incidents reported, the mistakes admitted, the honesty, the willingness to take on a conversation about what might go wrong, and things actually going wrong. And if you want to talk about psychological safety with your team, this is how you measure it. You can measure agreement with these statements, and the more agreement with these statements will indicate a higher degree of psychological safety. Now, we're not going to dive into all of these questions right now. These are all available on psychsafety.co.uk on my website. And if you want to find out more, just dive in there. What's interesting is that by asking these questions and asking people to agree with these statements, you're doing a number of things. You're surfacing any issues that impact psychological safety by identifying low scores. You're educating people about what psychological safety is. You're making it a safe thing to talk about. And you're encouraging the very behaviors that actually increase psychological safety, like admitting mistakes or finding systemic root cause. So yeah, go to PsychSafety to find out more. So to summarize, here are some ways, there are 8 ways to build resilience in your organization or team. First of all, build slack in. Build in the necessary buffer to facilitate adaptive capacity, because if you're too finely tuned, you're potentially too brittle. Manage cognitive load so that people can focus on the real problems of value, such as responding to unanticipated events, and size systems appropriately for the teams working on them. Pay down tech debt, because we all know what happens in systems with high technical debt. Increase observability and monitoring. And this applies to systems, internal, and the world, externally. People and systems cannot respond to a threat or a challenge if they don't see it coming. Embed practices and expertise in component cause analysis. Whether you call it a post-mortem, retrospective, or RCA, build those habits and expertise to routinely examine the component causes of failure. Run fire drills and disaster exercises. Not only are these fun, but they make it easier for humans to deal with emergencies and unexpected events. And that increases the cognitive load available for problem solving in emergencies. Structuring the team in a way that facilitates adaptation and change. Team topologies that facilitate resilience and increase organizational learning. And finally, creating psychological safety. It means that people can ask for help, raise issues, highlight potential risks, and apply their judgment without fear of repercussion. Because without those things, you won't have a learning organization. So to resilience engineering, we've really only scratched the surface. There are incredible experts in the field and vast resources to find out more. There's a link on screen at the bottom there to the Resilience Engineering Organization, which is a great place to start. Or you can contact me or many of the people that I've mentioned in this talk who will be more than up for a chat, I'm sure. Personally, I feel resilience engineering is the direction that DevOps is really going in. But that's not to say that DevOps is resilience engineering. They are different things. And so I'm going to leave you with this great quote from Heinrichs. Before you can engineer resilience, you must engineer the conditions in which it is possible to engineer resilience, which, if you remember the Submarine again, is exactly what David Marquet did on the Santa Fe. By empowering, emancipating, creating space for learning, psychological safety, and raising concerns and facilitating decision-making, he created a high-performance, more resilient, complex socio-technical system. So start talking about resilience, discuss cognitive capacity in your teams, do deeper dives in incident response and look for multiple component causes. Think about ways that you can increase observability inside and outside your organization and build psychological safety in your teams. So I think that's me done now, and I think I'm on time. Thanks for attending. Hope you find this useful and interesting. Get in touch via Twitter, LinkedIn, or email, or whatever. Now I think it's time for Q&A and then Eduardo's talk, which I'm really looking forward to.
Tom, maybe just great talk, and maybe just to guide us a bit further. So, what would be your first recommendation for an organization that is starting to look at becoming more resilient? You shared quite a few, but what would be your first one to go for?
Yeah, so I think with everything, it comes down to, well, I guess it depends who you are in the organization. If you're like one of us, a normal person, not the CEO, then start talking about these things. Start talking about psychological safety. Talk about cognitive load. Even talk about team topologies and suggest running postmortems and fire drills and those sorts of things. And you can start building that sort of stuff from the bottom up. This is how DevOps emerged, isn't it? Just by us doing stuff. So that's what I'd suggest. If you're a CEO, it's probably somewhat different, and you do actually probably need to start thinking about how to change organizational culture and organizational topology, which is a bigger deal.
Hi, thanks, Tom. And I'm not going to talk about team topologies. You already did that. I guess more of a reflection / question, because in the beginning we were talking about safety 2. I don't remember who came up with that term, but safety 2 as trying to get things going right more often, something like that. But then when we, the stuff that Sidney Decker talks about and the examples he gives, I kind of feel like it's the opposite, is having more failures, more kind of smaller failures more frequently, so you learn more from that, rather than having this idea that, well, we're going to be better or we're going to do things better. Yeah. Which is, I find, maybe counterproductive to think that you can actually do that because of the complex nature of systems today.
Yeah. Yeah, that's a really good point. So safety one and safety two, I think, are really they're kind of two sides of the same coin, but really useful concepts to remember because, and that's Dr. Eric Holnagel introduced that. So safety one is about looking at failures and thinking, how can we stop it happening again? So a lot of sort of aviation safety or crashes and that sort of thing that's where that focuses. Safety two is about looking at successes and thinking, well, we want more successes, so how do we make those happen more often? And of course, both are useful, both are applicable. It's also, you mentioned about small problems and small incidents, and the challenge there is, well, there's two challenges there. One is that if you purely focus on lots and lots of small challenges, you'll get good at mitigating those sorts of challenges. And of course, sometimes we get big ones like pandemics, and your capability in adjusting to small changes isn't going to do any good. In fact, it might actually do you worse, because if you constantly optimize for the small challenges and small failures, in fact, if you're adding to robustness, you're kind of, you've got a bit of redundancy here, a queue here, an extra queue here, another failover here. All of those things slowly build complexity and brittleness and actually make the system as a whole less resilient and less capable for change.
Let me see. Bibiana, do you want to ask them yourself? I'll read. It's on the chat. So, if a team survived Corona transition more or less without an issue, does it mean that the team is resilient? 100%, somewhat?
That's a great question. That means you're resilient against that particular challenge, which is great, but that's one particular thing that you're resilient against. You may well not be resilient against an earthquake or a market disruptor or a massive infosec breach.
Exactly. Yeah. And actually, there's another question also. How important, from the same person, how important is it not to point fingers, and how to avoid it during root cause analysis?
Fantastic question. Yeah, so that's absolutely critical. That's just like so it's so important. That's we call it by that name. We call them blameless postmortems. It's in most organizations. Well, in many organizations, you don't just call them postmortems. You call them blameless postmortems because the blamelessness is so important. If there's any indication that someone might have pointy fingers or blame, then you will not reach any of those component causes, and the process just will not work. And in fact, by trying to do it that way, you'll be making the team worse. Yeah, great question.
Okay, and I think one more. In this case, I have a hard time to talk about risk management and safety in my org. How does resilience work with scarcity, and how do we make the case of resilience in an organization?
Oh, that's a great question. How do we make the case for resilience? Well, I think it depends on your organization. In fact, Xavier, how does resilience work with scarcity? Could you clarify a little what you mean by scarcity?
Yeah.
There we are.
Perfect. Yes, just the many competing things that needs to be taken care of in an organization, right? Like there's always like more things to be done, and like urgent things usually have much more importance in how we talk about things, and specifically right now where like we might have had some approach before, but because of the current situation, like that brought everything up to a higher level. And so how do we? That's a bit of a struggle that I think we all have in our lives. But like, how do we make case for like the longer term, the resilient aspect of that, like the longer term, like things that might happen, and also the thing that could be like, oh, you think you have a hard time right now, but it could be much worse, right? We might want to mitigate that as well somehow.
Yeah. So great question. And this is common to so many organizations that either are or believe they are in firefighting mode all the time. And so if you're in that sort of team, what I'd suggest is you build some capabilities in learning, yes, but measuring unplanned versus planned work. So you can actually visualize and demonstrate how much effort and time is being spent on intentional value generating work and unplanned firefighting type urgent fix type work. And even more importantly than that is identifying the trend, whether it's up or down. What you may well find is that trend is slowly going up in terms of more unplanned work. And of course, at some point, you're going to have to do something about that, because that goes exponential, and then you get into a death spiral and everything goes wrong. So yeah, first thing I would do is start measuring that, and so you can communicate it to other people in the organization and say, here's something we need to do something about.
Sorry, I have my kids on my side, sorry. But my question is very simple. How to measure resilience? How do you know when you are sufficiently resilient or not?
Oh, that's a massive, like, I'll be honest, I can't answer that question, and I don't feel I have the authority to do so either. There are some fantastic papers by Sidney Dekker and Eric Hollnagel and similar people about how to do that. In fact, if you speak to people like Lauren Hochstein, John Allspaw, and people like that, then they'll be able to point you in more directions. But yeah, I would. That's such a huge thing, and it's very specific and context specific to an organization. So yeah, all I can really say is I can't answer that question.
Brad Appleton, you want to do it yourself, or should I read it?
You can read it. I've got a lot of background noise.
No problem. So on the last slides, with the list things of steps for resilience, does order sequence matter? Which things must come first? Psych safety versus which can be done in parallel?
Great question. I would say the order doesn't really matter. However, so personally, psychological safety is the fundamental enabler of all of those capabilities. Without psychological safety, or without a certain degree of psychological safety, you won't be able to do any of the other things, because you won't be able to effectively carry out postmortems or fire drills or pay down technical debt, because you just won't be performing. So build psychological safety. That's priority number one. All the others, go nuts.
Thank you so much again for the answers and for the great talk again.
Thank you everyone. Cheers.